Okay, hello, hello. Yes, I figured out the mute button. So hi, I'm ENG H Schlawack from Berlin. I work at a web hosting company called Vario Media. So this talk will be heavy on a back-end server side, which probably means this is the least creative talk you will see at this conference. It's also the first time I speak at a conference that is not directly related to Python, so I would like to just gauge the room a bit. So, quick show of hands, how many of you are involved with back-end infrastructure? Okay. How many of you use Python to some degree? Okay, about a half. Okay, I've got a lot of material, so poikrali, and let's talk about the goals of this talk. And by the end, I want you to be able to predict performance problems, so you can prevent them, because stomping out a blaze is a lot easier than fighting a huge fire. And if something happens anyway, I want you to be alerted by your system and not by a hysterical boss. And if a fire is burning, I don't want you to stare at the top output while your boss is poking their finger into your back, but I want you to have all the data about all your systems right at hand in a meaningful format, easy to query, easy to compute things out of it. And that includes historic development, because in post-mortem, you want to be able to reason about how you arrived at a certain situation. Now, if you want to reason about situations, you need an objective representation of that situation. So you can define a good status quo and also to describe a not so good operations fire. So, and you may have guessed what this objective representation is. It's of course metrics. And a quick intro, metrics are just numbers or samples that are time-stamped in a database. That makes them a time series. And you're gonna have a lot of time series, because once you start correlating data, it becomes much more useful. And you get those time series by adding instruments to your systems, just like in a car or in a plane. The twist is that your instruments are hooked up to some kind of time series database, or TSDB, and that stores them, and that allows queries and operations on top of the data. Now, how that exactly works and what you can do with the data depends on a metric system. Now, what you want to instrument is, of course, your app and your dependencies, like your database, your web server, your load balancer. They all carry very useful information for you to pick. Then you want to instrument your environment. You want to know the server load. You want to know how much memory is free. You want to know how much I/O is going on. And maybe you also want to instrument your business, because the number of customers, the number of paying customers, daily signups, daily revenue, this all can be useful, especially if you correlate it with, say, your front-end latency. So nothing of this is new. People have been doing this for years. I've been doing this for years. I'm sure many of you have been doing this for years too. But in the past, you had to choose multiple components with various trade-offs. And most notably, they were not integrated in any meaningful way. So for example, InfluxDB or Graphite have no opinions how the data comes in or how to monitor on top of them. They are just storage. Now others, like StatsD, are popular but more or less broken by design, because UDP tends to be one of the first things that turn to ashes once you are hit really hard, which are also coincidentally the moments you need metrics most. And that's even true for localhost. Now, Prometheus is different, because Prometheus tries to give you a well-rounded and opinionated metrics and monitoring system. It's still flexible how to get data in and how to get data out, but you will have a proven and well-documented starting point. And I know that opinions are a dime a dozen. In this case, they are valuable because it's more or less inspired by Google's internal monitoring system called Borgmon. And one of the reasons why they started this project was that ex-Google engineers were frustrated that they cannot have their favorite monitoring system in the free world. So let's have an architecture walk. Prometheus is just a single binary. You just drop it on your server, you add a configuration file, no other dependencies, works. Its central feature, of course, is storage. Effective storage of time series. So what exactly is stored? A time series for Prometheus is just a named stream of float samples with timestamps. That's the basic data type. Everything else builds on top of that. And Prometheus wants you to think in terms of 4 types. And the first one are counters, which are for counting events, errors, requests, whatever happens. And counters can only increase, but they can increase by anything because it's a float. So you can use it to measure your outgoing network traffic. Then there are gauges, which expose a number from your system. So you can set it to any float value, and it can be something like server load, temperatures, number of active requests, number of connections in a connection pool, or a timestamp. A Unix timestamp is just seconds since 1970, so you can perfectly store it there. Those two are pretty obvious how they map to timestamped floats. Now it gets more interesting. The summary takes measurements and allows you to compute the rate, so how many requests per second, and the average measurement, so for example, the average request time. Some clients, and Python is not one of them, also allow you to define percentiles on top of it, and they are computed within the app. I don't personally find summaries very useful. I don't use them at all, because you cannot aggregate meaningfully percentiles over time series. And I also don't want my applications to derive numbers while they are screeching and I need them to be really fast. So, which leaves us with the 4th type, which is the histogram. It's also about observing values, keeping track of averages, but additionally, you define buckets. And those buckets should have typical sizes for the values you are measuring. And Prometheus is then able to estimate percentiles from those buckets on the server side. And now I've said percentiles twice, so they are very important. And to ensure we are all on the same page, let me give you a quick refresher. And we start with the premise that averages are probably less useful than you may think. And let's have something concrete to talk about. So assume we measure request times. And I think it's fair to say that they are an important part of the user experience. Now, fast requests are good UX, slow requests, bad UX. And it doesn't matter if it's a web page or an API, it's always the same. And the problem is that the average time is not the average user experience. Because realistic data is usually skewed in some direction. There are no bell curves in production. So let's assume these are request times. Not only is 2.8 not the average UX, it also hides the terrible UX of the one request. So it muddles it all together, and if the average changes, you do not know how many users are affected at all. So you may be wasting your time on optimizing the perfectly good average instead of looking for the reason for a huge outlier. So what is the average UX here? It's 1, right? The average user gets 1 millisecond, let's say. So if you recall high school, there is a function that would have told you so, and that's the median. A median takes a sorted data set, and it partitions it in the middle, and it returns to the middle value or the average of the 2 middle values if you have an even-numbered set. Now, the median's strength in representing the average UX is also its weakness, because this still returns 1, which is not very useful too. But fortunately, where the median comes from, there's more. And now we come back to percentiles, because they also partition a sorted data set, this time in 100 parts. And now you look at the nth value for the nth percentile. And in practice, it means that the nth percentile, P, is the upper limit of n% of your dataset values. And to make it even more practical or intuitive, it means that if the 50th percentile is 1 millisecond, then it means that 50% of your requests are done by 1 millisecond. And if you think about it, that's actually our median again, which, as we've established, is not super useful by itself, but now we can look further because we have a parameter we can tune. So let's ask how long took the fastest 95% of your requests. And now you see two things immediately. First, the value is clearly an interpolation because we don't have 90,000 in our set. But we also don't have 100 values, so makes sense. But we also see on first sight there's something very wrong that affects only few users and not all of them. And let's look at a graph that's actually from production. From the bottom to the top, you can see the median in green, the 95th percentile in yellow or orange, and the 99.9th percentile in blue. And now there's, again, two things. First, the 99.9th percentile is a lot more volatile than the rest of them, which makes sense. It's the slowest per mil of all requests. There are so many reasons why 1 per mil of requests can be slow. But there also is obviously a connection between the median and the 95th percentile. So let's remove some noise. And what do these dents mean? So they seem to mirror each other. And they mean that the average user experiences improved because the time went down. But the slowest 5% worsened. Their times doubled or even tripled. And here's one dent that has no equivalent in the 95th percentile. So this means that the average got better, and if it got worse, which you don't know at this point, it affected less than 5% of your slowest requests. And these are all very useful information to have, because it helps you to reason about causes, and it helps you to reason about how many of my users are affected. Thing is, percentiles have one downside. They are rather non-trivial to compute. So good Prometheus does that for us outside of the instrumented systems. So back to Prometheus, and let's talk about metric naming. I think many of you have at least heard of Graphite, maybe even used it. And Graphite puts all the metadata into the metric name. Now, Prometheus, like all modern TSDBs, use bare name. And it's the best practice to prepend it with an app name and to append the unit, which total is used for counters. If you would have a timer, it would be, for example, seconds. Now, we add the metadata back using labels. So each new label combination still adds a new time series, or as they call it, a new dimension for the data. So you do not get less time series, but it's a lot more readable and it's structured, which is useful for aggregations. You can formulate queries on top of label values. You can use regular expressions on top of them. So this is much nicer to work with. And where do the numbers come from? And this is, I think, the biggest kicker. Contrary to most metric systems, Prometheus is pool-based. It means that each instrumented system exports its metrics via HTTP, and Prometheus scrapes them. So using the metaphor from before, you add instruments to a system, and Prometheus looks regularly at them, writes them down, and adds a timestamp. Now, that has a lot of consequences. One is that you can adjust the resolution of your data by configuring how often you let Prometheus scrape your targets. If you scrape more often, you get higher resolution, but it uses more disk space. It's for you to decide how precise you need to be. And then if a scraping fails for some reason, for example, the load is so high that there's a timeout, you don't lose data or meaning, you just lose resolution. So your average rates still make complete sense, which is the opposite of push-based, where a lost sample makes the rate actually sink. But in reality, the rate is rising beyond the capacity of the system. But in your metrics, it looks like it's falling. So this makes Prometheus great for monitoring, but it is kind of a bad fit for things like accounting, where you need to every individual value. That's not what Prometheus is made for. So in that case, you need something like Postgres or InfluxDB. Then there's a few problems. So short-lived jobs like backup scripts will not be able to hang around to give the metrics to Prometheus. The solution to that is called a push gateway, which takes the metrics push-wise from short-lived jobs and retains them for Prometheus to scrape. That's pretty easy. Then, of course, if you are scraping, you need to know what to scrape. There are two approaches. First, you can configure Prometheus. In this case, it scrapes itself, which gives you the number of time series or how it's using its buffers. Very useful to tune your systems. And a system you are scraping, a metrics endpoint, is called a target or an instance. And it's basically a tuple of a host name and a port number. And many targets together make a job. It's the same type of data together. Now, you get both of those automatically from each scraping target. And that helps you to keep scraping targets from each other. You can still aggregate them all together, but this way you get automatically a differentiation between your backends, for example. So the actual way you will probably go for that is using service discovery, and there's a lot of integrations for Prometheus. We use Consul, we really like it, but there are many other ways. Now there's a final problem, and that's that closed systems like Heroku or software that runs outside of your own network behind a firewall can't expose metrics to you. So Heroku is the best example. There have been talks about an official plugin, but there's nothing concrete out of it yet. Generally speaking, Prometheus is intended to run in the same network as its targets. Okay? So depending on the use case, I realize this can be a showstopper. So if that's you, feel free to leave, no hard feelings. I understand this is a use case that's not for everyone. But with that out of the way, there are, of course, advantages too. So for example, you can point multiple Prometheus servers at the same targets. That way, you get high availability, which is kind of important for metrics and monitoring. You can use your production data in your test environment. So for example, we had an intern working on some Prometheus stuff for us, and he ran Prometheus on his notebook, and we just gave him access to a few metric endpoints, and he got the work done without having access to our actual metric system. Then it's much easier to detect an outage if a scrape fails. You know immediately something is going very wrong here, which is not so easy on push-based approaches, where you have to reason about, okay, how long did I not hear from my targets? Is it just idle, or is it down? What I personally like most is that the impact on the systems is very predictable. So more traffic on your servers does not mean that you have more metrics traffic. So instead, see, if you have a request and you send out a counter, you're having more traffic. So, and under stress, I dare say monitoring and metrics are needed most. So if you start losing samples and your metrics turn worthless, they do that in the worst possible moment. Finally, instrumenting third parties is fairly easy, because most systems expose some kind of instrument, some kind of performance counters. Every database has tables with performance metrics. Every web server has a status page. Java has JMX. And you just have to transform those metrics into something that Prometheus understands. And turns out, what Prometheus understands is something you can understand too. Because each metrics endpoint has a human-readable representation. So this is a first part of a histogram for measuring request times. This is a terrible name for a metric, so don't call metrics like that. I just like using a big font so everyone can read it. And this consists of multiple time series. So first, of a counter, the number of measurements, how many samples has this metric observed, and then the sum of the measurements. So in this case, we had 390 requests that took 177 point something seconds. This is all Prometheus sees. This is super cheap to keep track of because you're just adding two numbers all the time. And I find it important because I do not want to add strain to my systems just to measure things. So by regularly scraping this, Prometheus can figure out the rate in which your requests are coming in, and it's enough to compute the average request time. And this is what you also get from the summary type in the Python client library. Now to get percentiles, we need the second part. We need the buckets. In this case, we have 6 buckets. The LE label defines the upper limit of those buckets. And the counter shows how many values are in this bucket. So they, of course, trickle down, because something that fits into 0.5 also fits into 2.0. And yeah, Prometheus now can interpolate percentiles from this. It's, of course, an interpolation, but it's good enough in practice. And you can increase the precision of those percentiles by using more buckets. But you just have to make sure that the values distribute kind of evenly over the buckets, because if all values are in just one bucket, Prometheus can't compute anything meaningful out of that. So we have metrics in our database. What do we do with them? We query them. And the Prometheus query language is called PromQL. And I don't have the time for a proper introduction, because you can do mind-boggling things like the game of life in it. But let's have a few examples. So first, if you have many related time series, you want to aggregate them to one or few. And that's where aggregation comes in. So say you have many backends in multiple data centers. And now you want the total request rate over all backends. So this is how you do it, and let's work ourselves out from the inside. So we take the counter, which you should remember from the slide before, and to compute the rate, the function needs a so-called range vector. This range vector returns the list of samples of the past 1 minute. And the rate takes the first and the last value of it and computes the rate from that. So you can affect how this rate is computed. Now we have the request rate for every single backend. And to aggregate them into one value, you just sum them up. So what if you want the rate of backends in one data center? Then you just add a label filter like this. This will return only time series that have the DC label set to West, and some will sum them up. And as a final example, maybe you want to know the rate of all data centers, but broken down by data center. Then you drop the filter again, and you tell the aggregation to retain the DC label. And that is done using the by clause. So this one gives you the as many time series as you have data centers, and the rate for each of them separately. So what else is interesting? Of course, percentiles. And Prometheus uses so-called phi quantiles, which is percentiles divided by 100. So this is the 90th percentile, and we take the rate of how those buckets are rising. And histogram quantiles will do the rest. So we have our percentiles. So once more, these percentiles are only an interpolation, because otherwise you need all the data to partition it. But if your buckets are good, then the interpolation is pretty good too. So I hope you have a taste by now of how powerful tool PromQL is, and let's look about the consumers of this API, which of course most notably is visualization. There's the internal one. It's not pretty, but at least it's not XJS. It's great for playing around, building queries, drilling into values, and then you just use the queries elsewhere. It allows only one expression per graph, so you cannot correlate really, and you can build dashboards using Go templates, but I wouldn't bother. There are better ways. One of them used to be PromDash, which has still the best integration, and it's the former official one. But since Grafana has merged Prometheus support, it's deprecated, so don't bother either. And that leaves us with Grafana. And I've heard already Wargaming is already using Grafana, so the good news is if you add Prometheus to the mix, you can still keep it, and it's the prettiest and most powerful one. And I really like that the many integrations, so you can have, you can build a dashboard using graphs from 5 different metric systems, and it would still look good and work. And this enables step-by-step introduction. So use this, but you already do. Which brings us to the final piece of the puzzle, alerting. And you can use PromQL to formulate alert conditions, and Prometheus will then push them to the alert manager, which will handle them. And let's use another example. And let's talk about monitoring for full disks. Because once a disk is full, it's too late. And if you alert on a threshold, that can lead to noise. And noise leads to alarm fatigue, which in turn leads to full disks. So let's use a crystal ball to be notified in time without the noise. And for that, we define an alert that will fire when the disk is full in 4 hours. And our crystal ball is actually more high school mathematics, and it's called linear regression. So in this case, if given the samples or the behavior of the system of the past 1 hour, you expect that the disk will have less than 0 capacity within 4 hours, and this estimation has been valid for 5 minutes, you want to be notified. The how is again very pluggable. So Alert Manager supports PagerDuty, email, but also webhooks, so you can get your alerts right into Slack. A final part of the architecture would be how to make this web scale. And the answer is federation. Prometheus servers can get their data from other Prometheus servers. So the typical uses for that is aggregation. So each team can keep care of one Prometheus server. Then you have a big one which just aggregates all the data from the whole company. Or you can use it for downsampling of data. So imagine you have one server with super fast SSDs, and you are scraping your targets very often, but you cannot store it for a long time because you're running out of disk space. Then you just use another server with more storage, and you scrape the faster one, but at a much smaller interval. And you can keep that for long-term storage. Okay, so now you have a general idea how Prometheus works. Let's focus on how to get the data in. And we will start with the environment. And the good thing is that Prometheus has been public for over a year, and as I've pointed out, it's pretty easy to write exporters for it. So there's a lot of them. Basically, each week is at least one is announced on a mailing list. And the interesting part is also the bridges, because this allows you to point your existing instrumentations at them, and then Prometheus scrapes those. So again, step-by-step introduction. You do not have to throw everything away. But of course, native is better. So let's start with the platforms. So for fully featured servers like Metal, KVM, LXC, you would use the node exporter, which instruments from the inside. It runs as a daemon on the host. And you know what comes next? For one process containers like Docker, you would use CAdvisor, which is from Google, I believe. They use the API, the container API to instrument the systems. So that works too. And once you do that, you get full system insight. You get your server load. You get your number of processes broken down by status. You get your free memory. You get your network saturation, free disk, and of course, the I/O load. So it's kind of important that you just put this into your automatic provisioning and then never think about it again. Another nice way to instrument system is to just follow a file and then compute metrics based on regular expressions. That doesn't sound very interesting, but in the end, there are some cases, like the Apache web server, where you get better metrics through a custom log format and regular expressions on top of it. So you should check it out. It's also nice for counting things like emails or something like that. So there's much more. If you want to look from outside but don't want to ping them, there are black box exporters. They will probe your system using HTTP, TCP, or even ICMP, aka ping. But they, of course, create additional load, so it depends on you if you find that tolerable or not. No matter whether you look at status pages or parsing log files, you should always instrument the outer edge of your infrastructure. So that usually means some kind of web server or load balancer. And finally, I can't imagine many applications without databases, and I believe most of the databases already have some instrumentation on GitHub. So, we now have detailed information about our platform. We know how to look at our app from the outside by analyzing logs or probing it. And we know that we can instrument third-party apps. It always depends what you're running, the how. So, assuming you instrumented your web server, you can already correlate request times with platform statistics and dependency metrics, which is pretty cool, but we need to drill deeper. And for that, we need to touch your code. So since I'm a Python person, I'm going to use Python, but there are official third-party integrations for many other languages. And as I've shown you, the export format is actually pretty easy. So you can do it yourself if you want it for your, I don't know. I don't think there's something for C. So if you want to, that's just C#. So let's assume you've built a groundbreaking product, software that determines whether a photo contains a cat. Now, you need to deploy it as an HTTP service, where the users post a picture, and you reply with meow or nope, depending on what the picture contains. So how hard can that be? Let's build a Flask web service. And you don't need really to know Flask or even Python to understand these few lines. So first, you check authentication, and because you read Hacker News, it's a microservice. And then you do your expensive computation to determine the contents. So now let's instrument it. And for that, we just use the official Prometheus client, which is kind of a first-class citizen in the Prometheus ecosystem. And before we change actual code, we do the least we can do, and we just start an HTTP endpoint. Because on Linux, you get instantly process statistics for free. So you have your memory usage, your process creation timestamp, your used CPU time, number of open files, and the maximum number of open files. So without further action, you can already detect memory and file handle leaks, and you can monitor whether we approach the file descriptor system limit. Now, let's start really instrumenting, and let's define some metrics. Each metric consists of a name and a help string, and you cannot skip the help string. They force you to write one. This is a gauge that will keep track of the number of active requests. Then we have a histogram that will measure the request times. And finally, a histogram that will measure the actual picture process time. And now let's add them to the app. And we just add these two decorators that do exactly what they sound like. The one is tracking how many function calls are in progress. The other is timing those function calls. And you might be saying that writing a middleware is better because then you get labels on top of the view name or the status code. And you'd be completely right. This belongs into middleware. But writing Werkzeug middleware is a bit out of scope here, so please indulge me. So additionally, we measure the time to analyze the picture, so we find out how big its impact is on the total time. Because for all you know, all the time syncs into authentication, which in turn ostensibly is not instrumented. And that's because it's a shared package. And let's instrument the package. Because if you have a library which is used in 10 applications, why should you instrument it 10 times? This belongs into the package. So again, we define a metric for the time spent and one for errors. I've already said it's a microservice, which makes it a distributed system, which means it will fail on you. Now, we retry, and I know that this is not the proper way to do retries in distributed systems, but again, scope, time. But we count the errors, and if this number goes up, if the rate exceeds, or if it should be 0 actually, but if this number is acting up, you know there's something really broken. And we also count invalid logins, because if they go up, it can mean you're under attack, or something subtle is breaking, and it manifests itself by failed logins, although something very differently is broken. So the name for these metrics will be the same in all applications. It's always auth seconds, auth error total, and so on. And you will differentiate them using the job and the instance labels I've talked about before. So if done properly, which means that you instrument your shared libraries and you put web-related metrics in the middleware, or even better, into your whiskey container, you're left with one extra line in your view, which I find tolerable. And you also should not be ashamed of instrumentation, because it pays off eventually, and nobody ever regretted to have too much information when their systems were melting. And now you may be asking, what about async? And if you're not, I do, because I like async, and that's why I wrote Prometheus Acing, that supports async I/O when twisted by doing the right thing if your functions return deferred or if they are coroutines. And it does that by simply wrapping the metrics from the official client. And it also comes with some goodies. So first of all, the actually Russian AIO HTTP-based metrics exporter, which is a lot more flexible and configurable than the one that comes with the official client. It can run in a thread, so it's useful with any Python 3 application. And it includes auto-registration for console agent. That's what we use. Service discovery is kept generic, so you can use your own. Well, I should say that it's not on PyPI yet, because I need to write some tests and I would like some feedback. So if you have some, please approach me. But it's on GitHub and we use it in production. So time for a wrap up. And let's look at the promises I've made. I've promised predicting problems. And if you have good, meaningful dashboards and use functions like predict linear or the super new hold winters extrapolation functions, you should be able to catch typical performance bottlenecks. So then there's alerting. We have the alert manager with its many, many integrations. We have PromQL, which allows you to define very sophisticated conditions. Done. And finally, a holistic overview. So if you instrument widely, as you should, you have the data. You can build dashboards. You can play with PromQL on top of Prometheus. You've got everything you need if the shit hits the fan. So I believe we've covered everything. I would like you to study a page I've set up, which contains all the links all the projects, and so you can dive into topics I could only brush over, because 40 to 45 minutes is short. And yeah, follow me on Twitter, and if you speak German, get your domains from Variomedia. Thank you.
Thank you, Hinek, for really interesting and comprehensive lecture. And we got approximately 10 minutes for a Q&A session. So if you got any question, please feel free to stand up to the microphone, or maybe we can approach and ask you personally. Можно задавать вопрос на русском языке.
You can also ask questions in Russian. Either way, you're welcome.
Oh, hello, and thank you for the session. I got a question for you regarding your example in Python. If I got that example right...
Wait. Which one?
Yeah, the entire one, basically. If I get it right, and if you run your application in a WSGI container, you'll probably get different numbers in every single worker.
I get
right?
what?
Different numbers, I mean different matrix values in every single WSGI worker.
Yes.
So what's the reason to do that? And how do you query every single worker, especially if it gets reloaded after a certain number of requests?
Are you asking about how you get the metrics out of those workers, or how you query the data?
How do you get that matrix values out of your application and get it to Prometheus? And should it query every single worker by itself? How do you do that? How do you do that?
So the production way is to use service discovery. And you can use something like etcd or console or just DNS.
I'm sorry, you got a box running your application in USGI. You get 32 USGI workers in that box.
Yes.
Every single worker collects that matrix in its own fashion and stores inside that memory.
Yes.
So you
it's not much data though, because it sums the data up.
Yeah, but you got 32 different independent set of values. How do you consolidate that into the Prometheus?
So you would, so to get into Prometheus, you really just use some kind of service discovery, which tells Prometheus, here are the targets, get them. And I think your bigger question is how you work with the data.
No, no, that's not the question. Look, if you report to Prometheus, like, please query that host and port for matrix, for your matrix, and you have your application here, you'll get random USGI worker to respond, and it will respond with their values it's stored inside exact that worker and not that application on that box.
Okay, I think I'm starting to understand what you mean, but what do you mean exactly by a worker? Is this like a micro WSGI process with its vessels, or do you mean like a Docker container?
Not a container. I mean, where this, say, request time metric you define in your code, it stores the values inside the memory of that process, right?
Well, each process is going to store its own metrics, and then it will expose them over a port. So I personally use random ports. So I just say listen 0 and send, and then look at the port and tell Prometheus, here's a metrics endpoint, please get it from here. You do not. So there is some work in the Python client to do cross-process metrics to some degree, which I personally don't use. I just expose each worker, each process has its own metrics, and then I aggregate it in Prometheus.
Well, that means if you have the setting for your worker that after every 1,000 requests, it should stop and reload, that means that you, do what?
For that, I use uwhisky.workerid as a label. So you have just a number of workers, they keep coming back. So you have an ID, which is just a number from, I think, from 1.
Okay, thank you. I got it, but that makes it unusable, sorry.
So we got, I believe, time for one more question. So, Alex. Or maybe 2.
Агрегирует ли он исторические данные? И в какое время там или как-то это можно настроить?
Does Prometheus aggregate historical data, or how can we track it?
When you say aggregate, do you mean like that it does like the aggregation over time, that it starts rolling up? I think roll up is the right word here.
Ну, понятное дело, если мы каждый там time travel храним, да, и накапливается все это дело, то есть историческая точность нас такая не интересует. Возможно ли там как-то агрегировать это?
If we collect too much historical data, does it concern piling it more and more? To what degree?
Yes, so it's what he meant. So Prometheus does not have internally a way to say, I want the last 1 day per minute, and a week ago just per hour, and a year old data to roll up to our daily average. You can simulate something like that using federation. As I gave an example, that you have one really busy worker which has a data set of, let's say, a few days, and which then gets downsampled to another server in a much smaller resolution. But it's really just streams of data, and you cannot say, like in Graphite, that you want this data to aggregate over time. Which, by the way, InfluxDB doesn't either, and OpenTSDB also. So it seems that Graphite is the only one who can do this really properly, that you say that you want the data to aggregate over time.
Any questions?
So I believe if there are no more questions, then we should say thank you to our speaker today. And we've got a few minutes for a coffee break for the next session. Thank you, guys.
Thank you. Thank you, Hinak.